So, let's talk a little bit about this unit. For this unit, you need to be able to write formulas for ionic, covalent, and acid compounds. Sound familiar? For this unit, you have to be able to use those formulas to write reaction equations. With those reaction equations, guess what you have to do? Balance them. And then we're stepping back, way back, into when we were doing all those molar calculations.
Those are fun.
So we are getting into using T-tables with everything you've known about reaction equations, combining it, throwing it all together, and calling it stoichiometry. So you kind of see that this curriculum is continuing to progress. It is snowballing on itself. This is why I keep slowing down and making sure that you have everything down before we move on. You will have to demonstrate that you know all of this as we go about the rest of this quarter. Questions? So the first thing you need to do for me is draw your mole map.
Could we just draw this whole entire thing so it's in the table?
Yeah,
Kinda
sorry.
skip that.
What? Stupid.
Hey, so back to your mole map. What do you remember about it?
Grams to moles is particles.
Okay, yeah, good. So, you remember that we have grams, we have moles, we have particles. Do you remember how to get between all of those?
Well, they're trying to say it's wrong.
Somewhat?
Avocado.
Avocado's numbered.
Yeah.
Molar avocado.
Alright, so yeah, you got bits and pieces of it. Hold on. So, here is what you should remember from before with your mole map. I have grams. I can go from grams to moles using what?
Molar mass.
Where do you find your molar mass?
Periodic table.
Yeah, we're using the periodic table. Now, how would you find the molar mass of a compound?
It's hard.
Add up all the atoms. So if I have O2, each oxygen is 16 grams per mole. So times 2 equals 32 grams per mole for O2. Now, I can go from moles to particles. Now, most of you guys remember going to what unit here? Atoms. Atoms describe individual elements. If we're talking about particles, atoms is a type of particle, but we are going to be focusing on different compounds here. And for compounds, we have two other terms that you need to remember. For covalent compounds, we call them molecules. Molecules. For ionic compounds, we call them formula units. Okay? So, don't be confused by those terms. They're all particles, but they describe different things. However, it's the same way to get to all of them. 1 mole is equal to what? 6.022 times 10 to the 23rd. So, if I'm starting out with so many grams, let's just use a variable here, x grams. I can go to moles using my molar mass. Let's just say I'm using another variable for molar mass because I don't really have a compound in mind right now. Let's just use my molar mass of this compound is y grams per mole. Now, if I take my next section to go down to particles, I know that 1 mole is equal to 6.022 times 10 to the 23rd particles. This represents the work required for any general mole conversion that we've covered so far? What are the only two things that you really have to change in any question I ask you? No, units are typically going to be the same. The amount of grams we start with, or whatever the amount is that we start with, and what else? The molar mass based on what substance we're using. So those are the only two things that really change here. Everything else keeps the same format. Once you get good at mole conversions, I told you before, it's going to feel like you're doing the same problems over and over and over again, just applying slightly different numbers. So here's stoichiometry in a nutshell. You know what? I'm not even going to tell you what stoichiometry is. I'm just going to show that you can already do it. Now, my wife and I like to have bonfires at home. And every time we have a bonfire, she likes to get out graham crackers, typically 2 graham crackers. She puts a roasted marshmallow and 2 pieces of chocolate between the 2 graham crackers.
That's how you're supposed to do it.
What?
She was saying that's how you're supposed to do it. She's complimenting it.
Oh. So with this ingredient list, she makes a graham cracker sandwich. A what?
S'more. Don't say some more, say s'more. Because it
I have no idea what you're talking about. I've never heard of that in my life. So, this graham cracker sandwich consists of 2 graham crackers, GC2. It consists of 1 marshmallow, MA. And it consists of 2 pieces of chocolate. So you make a GC2MaCH2.
A s'more?
A graham cracker sandwich. Now, does everybody see how this represents a reaction equation? Hey, I know we're hungry. Let's focus though. Here's a reaction equation where I'm putting together 2 graham crackers, 1 marshmallow, and 2 pieces of chocolate to get a tasty, delicious graham cracker sandwich.
S'more.
Tell me this. Tell me this. If I have 10 graham crackers, how many graham cracker sandwiches can I make? 5. How did you know that?
You have to use 2 crackers per sandwich. It's a sandwich. You need to.
Interesting. Interesting.
You can make an open face sandwich.
Hey, no, we're using this formula up here, this reaction equation. Now, what if I had 20 marshmallows? How many graham cracker sandwiches can I make? 20 GC2MaCH2. How did you get that?
Common knowledge. Common sense. Because we are fat.
Ah,
We like
you need to think, hey,
cracker sandwiches.
guys, you need to think about how you are getting this, because it's the how that you're overlooking right now, and that is how we're going to do stoichiometry here shortly.
You divide. You do like however many you have divided by like the original.
But how do you know what to divide by?
Whatever.
Whatever the original problem is.
All right, let me do another one. If I have 8 graham crackers, how many marshmallows would I need to use up all my graham crackers?
4.
I would need 4 marshmallows. You guys are actually using something right now mathematically that you are not recognizing. No. What are you using?
Division.
2 graham crackers here is equal to 1 marshmallow. What are we using? We're using ratios. We're using ratios here. And you guys will continue to use ratios for every reaction equation that you balance and try to do stoichiometry with. So what if I put another term here, 2 moles of graham crackers is equal to 1 mole of GC2MaCH2. Where did I get the 2 moles and where did I get the 1 mole?
I have a
2 GC, 1 GC2MaCH2.
When you make the sandwich, it's considered like something.
It's considered one thing. It's implied you have one of them if nothing's written in. So here, all I am using is my balanced reaction to get my mole ratios. So, back to our molar map. When we're dealing with the reactions, we're not just dealing with one compound here. We're dealing with 2 different compounds inside of a reaction equation that could have many compounds in it. So, when we're comparing or trying to quantify how much substance is made in a reaction or how much substance is used up in a reaction, it doesn't make sense just to have this one side of your molar map. We need to compare 2 things, so we need 2 sides to our molar map.
It's not hard.
Here, orange represents compound 1. Yellow represents compound 2. What you should see is that it is a mirror image. The only difference here between the molar map you have and this new molar map is that link between the 2 compounds, which is what?
Molar ratio.
The molar ratio. This is where we are using our balanced reaction equation to get a ratio between the 2 things we're talking about. So, take a look at this problem. How many moles of oxygen are produced when 3 moles of potassium chlorate decompose completely? Well, take a look at the reaction equation above. First step here is to balance it. So, I should have 2, 2, 3 as my coefficients when it's balanced. Now, the 2 things I always tell you to do is figure out what you're starting with and what you're going to. So for this problem, what are you starting with?
Starting with 6 oxygen?
No. You're starting with 3 moles of potassium chlorate. You always start with what is given. Typically, questions always ask what they want you to go to first. How many? No. It's asking you for moles of oxygen. So we're starting with moles of potassium chlorate. We're going to moles of oxygen. So I start my T table off, 3.0 moles of KClO3. Now, jump back to your mole map. Here's what I recommend you do for every single problem until you have this memorized. Put 2 fingers on it. So, if we were going to put a finger on where we start, we would put a finger right here on moles of compound 1. If we put a finger on where we end, we would put a finger on right here, moles of compound 2. How many steps is this problem? 1. And what do you need? The molar ratio between potassium chlorate and oxygen. So, what's your molar ratio between potassium chlorate and oxygen? 2 moles of KClO3 equals 3 moles of O2. So here's my T table. How do I plug this in to get moles of KClO3 to cancel out? So 2 moles of KClO3 on bottom, 3 moles of O2 on top. Moles of KClO3 cancel out with moles of KClO3. I'm left with moles of O2 as my units. 3 times 3 is? Try 9. 3 times 3 is 9. Divided by 2, 4.5 moles of O2 is your answer. Take a look at the next one. You're balancing here. 4, 5. That gives me 13 oxygens. So 6.5 and 1. I don't necessarily have to multiply by 2 here to get rid of the half because ratios are ratios. A 6.5 to 4 ratio is the same as saying a 13 to 8 ratio. So, where am I starting? Where am I going to?
You start with 88 grams of O2.
Start with 88 grams of O2. Where am I going to? Grams of CO2. Go back to your molar map. I'm going to put a finger on where I'm starting and a finger on where I'm going to. Where am I starting? Grams of compound 1. Where am I going to? Grams of compound 2. How many steps? 1. Use my molar mass. 2. Use my mole ratio. 3. Use my molar mass. That is your challenge right now. Write a T-table going from 88 grams of O2 to figure out how many grams of CO2 is produced. So we're starting off with 88 grams of O2. Excellent. First step is molar mass of O2. No. 16 plus 16 is 32 grams per mole. So I put my 32 grams on the bottom, 1 mole of O2 on top. My next section is my molar ratio. What is the ratio between O2 and CO2? 6.5 moles of O2 to 4 moles of CO2.
Oh, so you keep them connected like that whenever you're doing like from one side to the other? Wait, then would it be 32 on the bottom and then 1 on the top?
No. So, again, the balancing, whether you multiplied everything by 2, it would be 13 to 4 or 8 versus 6.5 to 4. It's the same ratio. But your last step is the molar mass of what? Not O2 now. Molar mass of CO2. So the molar mass of CO2 is 32 for your 2 oxygens plus 12.01. 44.01 grams of CO2 for every 1 mole of CO2. So, I just added 1 carbon and 2 oxygens. So look at my units. Grams of O2, cancel out grams of O2. Moles of O2, cancel out moles of O2. Moles of CO2 with moles of CO2. I'm left with grams of CO2. Everybody have their calculator out? Somebody calculate this. 88 divided by 32 times 4 divided by 6.5 times 44.01. What? 75 grams of CO2 is your answer. So what question did you just answer here?
How many grams of O2 are produced from 88 grams of O2 I have to with my explicit routine?
Yeah, so basically it's saying if I start out with 88 grams of O2, I will produce this much CO2.